Fernando, thank you to all the participants to joining us. Impressive number here I see on the screen. And yeah, I'm trying to do the impossible to summarize a 3 years project in 3 minutes. But at least I have the pleasure to give you an heads-on and an overview and what we are talking about in a nutshell. So ReFreeDrive is part of the Horizon 2020 research framework funded by the European Commission to provide research, development, innovation in the European community, in the European industry. We have been selected in the green vehicle, the GVO4 call, together with 2 other projects, which are joining us in some workshops at also on LinkedIn. So if you're interested, you will also see what they're working on. Our goal, in a nutshell, is to avoid rare earth magnets in next generation scalable electrical drivetrains. As I said, this is a 3-year project, has been anticipated to finalize in September 2020, but obviously due to activities stopped now under Corona situation, we will ask for a project extension with a question mark. So we might run another 3 months, 6 months, I don't know, in order to present the final results. There are 13 partners from 6 European countries joining the project consortium. Today, on the very left, we have speakers from University di L'Aquila in Italy, from Motor Design Limited in the UK, and from Institut Français Pétrole Énergie Nouvelle in France, presenting the design optimization. Other partners involved in power electronics integration, copper, as ourselves, of course, with the member Rubis and Breukman, will hopefully also contribute in later sessions and webinars. Why are we so keen to avoid rare earth elements? Well, there are supply issues, there are cost issues, there are market uncertainties, and nevertheless, there are environmental LCA issues. Supply risk. If we talk about rare earth permanent magnets for electrical vehicles, on the upper right, we see the 2 elements, neodymium, dysprosium, which are the main elements used in today's permanent magnet machines. So but they're not only for electrical vehicles, they are also highly important to other green technologies like wind turbines or others. So there's a increasing demand all over the place. And on the other hand, so they're not only up there, they're also very far right there, because the supply base is very much limited and concentrated in Chinese hands. Over 95% or even more are coming from China. The costs are an issue, obviously. So the cost proportion, depending on which study you're citing, are a significant part of the total motor costs. There is market uncertainties, which is even more important than the absolute cost. So we had a price peak in 2011 for neodymium dramatically, because Chinese supply export to abroad was periodically stopped or limited. So there's a high uncertainty how this can evolve and how this can affect that, of course, long-term supply contracts. And nevertheless, the environmental and LCA issues, these elements like neodymium have a high global warming potential, so a relatively negative CO2 footprint, and there are other issues like recycling, recovery, still unsolved. But of course, you can ask, okay, what about other elements? I mean, do we run from one criticality, avoiding neodymium, to another criticality if we put more copper into the motor? Well, short answer, no. Copper is not a critical material. Today, you see it on the right side of the chart, there's at least 30% of copper coming from recycling, from the secondary route. In some regions like Europe, this could easily go up to 50% or even more. There are still a lot of reserves, discovered reserves, but a lot also of resources and discovered resources, which, according to geological analysis, provides up to 250 years of copper. Main objective of ReFreeDrive is not only to fulfill an academic task, but we will prove that our solutions, which avoid rare earth elements, are industrial feasible, can be easily transferred to mass production, and ultimately also save costs. We do this by a clever material selection. We analyze the impact on the manufacturing processes. There is design optimization, which is the main topic today of the three speakers following. And we also tend to present a scalable solution. In total, our project will develop and manufacture a physical 8 different e-motor prototypes. There are 2 induction machines, one with a fabricated copper rotor, one with a die-cast copper rotor, and there are 2 versions of the synchronous reluctance machine. One has permanent magnet, but these are not rare earths, but these are low-cost ferrites, so no critical materials. And the second SynRel technology doesn't use any magnets in the motor core. And we will present the solutions for 2 power classes, 75 kilowatts and 200 kilowatts. And as I said, our solution is scalable, so we could theoretically realize any power motor class in between. Our main benchmark when developing the proposal for the project was the Tesla S60, which is an induction motor, but with a relatively high volume and a good awareness in the market. And we intend to be 30% better regarding specific torque of the motors. We want to reduce the direct motor losses by 50%. So meaning we're aiming for a motor efficiency of 96% plus. As said before, cost reduction in mass production is an important issue. 15% is a target, and ultimately 50% increase of power density in the power electronics, also to offer a relatively compact package. Now, design optimization has been finalized. We have started to manufacture the 8 physical prototypes, which is somehow on hold and or slowly now going on. But all these 8 prototypes, induction and SynRel, 75 kilowatts, 200 kilowatts, will be then tested on motor test benches. And in a later stage, also at least 2 of the 75 kilowatt motors will be integrated into a standard LCV and tested under driving cycle conditions at Perugia circuit in Italy. We hope to show real test results towards the end of the year, in order to prove what now the 3 speakers will present at the calculated performance also proves in real life tests. You can find much more information, latest scientific papers we published or presentations on our website, www.ReFreeDrive.eu, and also on the LinkedIn cluster page we joined with the other GBO4 projects. And this is number 1 today of our planned webinar series. So we will talk about motor design. There are other topics on the agenda for further webinars: power electronics, the manufacturing process, of course, the real test bench result, techno-economic analysis, and ultimately life cycle assessment. So stay tuned with us, and hopefully you can join to one of the next webinars as well. Thank you.
Great. Thank you very much, Thomas, for your quick but efficient introduction. Hereby inviting Mircea to start sharing your presentation. And meanwhile, I will invite the audience to respond to our first poll. 2 questions relative to the introduction made by my colleague Thomas. So first question is, compared to other hot topics for the automotive industry, how do you see the relevance of avoiding rare earth-based permanent magnets? So is it really high in the agenda or rather marginal or so? So we would appreciate your views on this. We will comment on the results afterwards. And second question is, what are the most promising ways for the automotive industry to address the rare earth supply challenge? So we offer here several options, such as using less critical rare earths, such as cerium and others, reduce the amount of heavy rare earth elements in the magnets, explore alternative permanent magnets with non-critical ferrites, and develop alternative technologies not based on permanent magnets. So thank you for your votes. And at some point, I think we will finalize in a few seconds the votes, and we will share the results. I think the trends are stabilizing. Okay, very good. So in order not to take more time, I will stop here the vote. This is very quickly the result obtained. We will comment on the results later on. Now, I will give the floor to our colleague, Mircea. So Mircea, the floor is yours. You can go ahead. Thank you.
Thank you, Fernando. Hello, everyone. So I'm going to talk a bit on the induction machine solution that was part of this project. So we are going to cover a quick introduction. Then I'll show the specifications that we had to address for this, all the designs that we had in place, and how we tackle the design workflow for the induction machine, briefly on the electromagnetic design, thermal, few words about prototype, and then conclusions. So as Thomas mentioned, development of next generation of electric powertrains and for automotive industry require a focus on a rare earth free traction solution. An induction machine is one of the potential candidates for such solution. And what we did, we thought about using a solution making use of a copper rotor, because this will ensure that we have higher efficiency, because copper has higher conductivity as compared to the aluminum. It will run at a higher speed. This means that we will be able to reduce the volume and the weight of this machine while delivering the same required power. Trying to maintain the low-cost manufacturing, we look at two possibilities to build the cage, copper cage of this machine. One, it's using die casting procedure. The other one, it's a fabricated solution. For the winding, stator winding, we decided to investigate the hairpin winding technology. I'll mention briefly why we did this. And then looking at different low cost and materials. And last but not least, we optimized design while considering as well cooling of this machine. These are the specifications valid for all the machines designs that you'll see today. They are based on specifications coming from Jaguar Land Rover, the OEM partner in this project. And you can see the target vehicle was this Jaguar XJM Y21 with the different performance requirements listed here. Cooling as well, and power electronics. What is important to note, I'm not going to go through all the numbers, but it's important to note this value. So peak torque, 370 Newton meters, peak power, 200 kilowatts, maximum operating speed up to 20,000 RPM, cooling system using liquid cooling. In our case, will be a water jacket with spiral cooling. And from the supply point of view, you notice we have the availability of a high voltage, 650 to 720 volts, while the current available from the inverter, it's up to 500 amps RMS. While the envelope of the of this design, it's listed there, diameter of 250 millimeters for an overall length of 325 millimeters. Further, obviously, this project is supposed to improve upon the existing solution on the market. and we took as reference Tesla 60S motor that is used in the Tesla vehicle, for which you can see the specifications given here: specific power, power density, specific torque density, and peak efficiency, and what we have to achieve with reference to the Tesla vehicle. So what we did to get our design, we are making use in these calculations and optimizations of two tools, MotorCAD and OptiSlang. And the reason to do this, because they are fast and accurate, and will help us in getting an optimized design for this induction machine. The process it's illustrated in this slide. So we'll start doing initially a sensitivity analysis. Based on this, which is point number 1, based on this, we'll get a meta model from which we can investigate influence of different parameters over the performance of the machine. And then we optimize and get a solution that we validate using specific calculations, puncture validations, using the software that it was mentioned earlier. So from the optimization design workflow, we have tackled and considered in the same time 2 aspects of the machine performance. One is the electromagnetic performance, and the other one is the thermal performance. How we model the performance of the machine: magnetically, we make use of the equivalent circuit that it's given there. It's a standard T circuit. You can recognize the elements of a per phase equivalent circuit for an induction machine, which all the elements there are calculated using either analytical algorithms or finite element procedures. From the thermal point of view, we made use of a lumped parameter thermal network that it's given in that lower right diagram. For each candidate design, it takes about 10 minutes to calculate the performance, and the meta model was making use of 400 candidate designs, upon which we have generated later an optimization solution. From the because we are discussing about an automotive application, we have to consider a certain drive cycle. And in our case, we decided to make use of WLTP3 drive cycle. This is a world harmonized low duty cycle vehicle recognized worldwide. And how did we make use of this drive cycle? This drive cycle has 1,800 points to consider, so it takes a lot of computational effort to take all the points into account. So we decided to pick few clusters. You notice from the color code, we picked 1 point for the high-speed solution in what is the pink area, high speed, another point for medium, 1 here at the low rotational speed. And as well, we considered 2 other points at a relatively low speed, but with the medium and high torque demand. Then from the electromagnetic design point of view, you can see on this right now on the screen the solution that we have selected in the end. It's a 4-pole machine with 36 stator slot and 50 rotor bars. The rotor bars are closed, while for the stator, you notice they are all parallel slot because we are going to use hairpin winding. For the design of this machine, we investigated and considered different electrical steel materials given there from thin gauge steel NO3015, which is 0.3 millimeter thickness, NO20, 0.2 millimeter thickness, M23535A, which is 0.35 millimeter thickness, and M29050. Based on this analysis, we selected the M23535A, given as well on this slide as the final solution for the electrical steel. For the copper materials, obviously the winding is made of pure copper. But for the rotor cage, two materials, copper ATP for the die-cast solution and copper silver 0.04% content of silver fabricated rotor cage. Some details about the turns per phase. There are 12, and the packing factor, which is the slot fill ratio, meaning copper area over slot area, it's 0.73. From the magnetic point of view, to optimize the design, we considered few certain parameters to optimize, and they are given here. You notice we look at the active length, mechanical air gap, split ratio, which is the ratio between stator bore and stator outer diameter, slot dead ratio, width ratio, bar opening depth, bar depth ratio, bottom bar, and top bar width ratio. And with the images illustrated on the right-hand side of this screen. Important to note, we had to, in optimization, it's important to use these ratios to make sure that all the geometries are feasible. And these are the results from the magnetic point of view. What you see here, we have efficiency maps, torque versus speed with the efficiency loci on the left-hand side and power versus speed on the right-hand side. And we noticed that we achieved the torque demand without any problems. The required 200 kilowatt output power, maximum output power, is achievable for quite a large speed range from about 5,000 RPM all the way to 15,000 RPM, with a short peak up to 300 kilowatts. And the efficiency, maximum efficiency for this drive cycle was just above 95%. From the thermal point of view, the cooling of this machine, it's achieved using a combination of cooling paths. One circuit for the stator jacket, which on the screen is colored in dark blue. And we also connected in series this circuit with the circulating fluid through the shaft, and a similar cooling system to what you see here on the right-hand side, the cooling system from Audi e-tron. So series connection between the two cooling systems using water ethylene glycol mixture, 50-50%, while arranging these parameters: housing thickness, water jacket wall thickness, channel width, spiral groove channel height. This refers to the shaft cooling, and the flow ratio, flow rate ratio. The thermal design was giving us what you see now on the screen. This is what we call continuous performance, meaning that the machine is capable of delivering the performance without exceeding 180 degrees centigrade for the stator winding and 200 degrees centigrade for the rotor bars. So you notice that this machine is capable of delivering continuously peak torque of just above 160 Newton meters and continuous power of above 120 kilowatts. On the prototyping, we are making good progress, even given the actual conditions with the coronavirus. We still the consortium managed to build different elements of this machine. What you see here is the stator assembly with hairpin winding, courtesy of Technomatic. It's a winding with 4 conductors per slot, and you can see also we have installed thermocouple, so then the temperature of the machine can be monitored. From the rotor point of view, courtesy of Breugmann, you can see here copper die-casted copper cage with the rotor package in there. On the right-hand side, we have elements of the shaft through which that I mentioned already. Through the shaft will circulate as well fluid for cooling. Also, the inverter box was manufactured, and in the end, the machine is supposed to look like that graphical illustration on the right-hand side. So the inverter box will sit on the housing of the machine, and this will be assembled for the test stand. The testing will be done in France at IFPEN, and as well at Privé in Italy and South in Spain. Conclusions. We look briefly into a solution for a 200 kilowatt peak power 20,000 RPM copper rotor induction machine for a traction application. Optimization was achieved using ANSYS MotorCAD and ANSYS Suite software, and the solution comprises hairpin winding, die custom fabricated copper rotor cage, and the series cooling fluid circuit for the shaft, stator, and inverter box. The optimized motor is currently prototyped, and hopefully we'll be able to test it later this year. And the same design is scaled, can be used for a 75 kilowatt, 12,000 RPM for integration in a lower power vehicle powertrain. Thank you for your attention.
Great. Thank you very much, Mircea, for your interesting presentation on the induction motor design. Hereby inviting our next speaker, Andrea Credo from University of Aquila, to start sharing your slides. And meanwhile, we invite our audience to submit your votes on 2 questions. First question is whether you think that an optimized induction motor can compete well with rare earth permanent magnet motors for EVs. So let's see, Mircea, how convincing you have been. And second, which features of the induction motor design presented seem most valuable to you? So here we go through the multiple strategies followed by the project. So let's see how our audience finds more or less valuable any of these avenues. So we will leave the poll open just a few more seconds, and then we will finalize the vote. So let's go ahead. I think this is converging now. This is the result, and we will have the chance to comment about it later. So now we can go back to the presentation. Thank you everybody for your votes. And now, Andrea, the floor is yours. Thank you. You can unmute yourself.
Thank you, Fernando. Good evening to everyone. I am Andrea Credo from the University of L'Aquila in Italy. Today, I will present the design flow and the results of the pure synchronous reluctance motors as a part of the European project ReFreeDrive. The presentation starts with a short introduction of the pure synchronous reluctance motor. Then, the requirements will be presented. A specific design workflow has been adopted to reach the performance required for the application, starting from the preliminary design. After that, different optimization procedures have been used, such as the topology optimization and asymmetric solutions, including multiphysics analysis. Finally, the results, the picture of the prototype, and the conclusion will be discussed. The synchronous reluctance motors are characterized by distributed stator windings and by the motor need of a brushless AC control with a vector control. In this figure, the main elements of the synchronous reluctance motor are presented: the radial ribs, the tangential ribs, the flux barrier that create the magnetically accelerating rotor, and on its anisotropy will depend the torque available from the motor. Therefore, in order to satisfy the high requirements imposed by the application, it is necessary to achieve a high magnetic saliency. The synchronous reluctance motor could be a valid alternative for electric and hybrid vehicles due to its simple and rugged construction. It has been selected for this reason as a rare earth-free motor solution for the next generation of the electric powertrains. The general advantages of the synchronous reluctance motor are the absence of the windings and magnets in the rotor that allows to have low inertia and so good acceleration performance, and less requirement for cooling, because the losses in the rotor are smaller than the ones in the other types of machine. Moreover, it is attractive from an economic point of view, making it very suitable for household and consumer appliances, because it's easy to manufacture. The disadvantages respect to permanent magnet motors are a lower power-to-weight ratio and a lower power factor. It requires an accurate design in order to reach very high performance and complexity in control. Like permanent magnet motors require a field-oriented control, but it has a non-linear torque current behavior. This is the design flow used for the synchronous reluctance motor. After the assignment of the requirements, it has been possible to design and optimize different solutions, changing the number of slots and poles. After a great number of solutions of combination has been evaluated, the best candidates have been optimized from an electromagnetic point of view. The optimization has been done for all the best candidates because the performance of the synchronous reluctance motors strongly depends on the optimization procedure. After that, the best solutions has been chosen, and for that, a refinement ensuring the rotor mechanical integrity at high speeds has been realized. Then, the electromagnetic and mechanical optimization are presented, and after that, a design refinement has been made, which includes the introduction of an asymmetric rotor in order to minimize the torque ripple. Then, the evaluation of the performance of the final design has been carried out. Finally, the prototype has been realized. The requirements are based on the Tesla Model S, with an increasing of the 30% of the performance. The requirements are the same of those my colleague showed in the previous presentation, but it is worth noting the high specific peak torque and the peak power for the type of the motor, the synchronous reluctance motor. In this table, there are further requirements imposed by the application that use the Jaguar XJ MY21 as target vehicle. The car has two motors, one for each axis, and the dimension of the encumbrance consider also the housing. To reach these severe requirements, the fluid shape barriers have been chosen in order to improve the overall performance of the motor, because they offer a very good saliency ratio and reduce the torque ripple. Moreover, the fluid shape is easy to optimize, since it requires less variable, because it already is an optimized shape. The figure shows the solution for the 4 poles, 30 slots, the 6 poles, 54 slots, and the 8 poles, 72 slot solution. The figure shows only one pole of the machine. The table shows the results obtained from the optimized designs of the synchronous reluctance motors. The best values are circled in green, and circled in red, there is the worst values. All these solutions are able to match the requirements presented before. All the solutions have the same peak torque at base speed of 430 Nm and the same maximum phase current of 700 ampere, because these two values has imposed as constraints. The six-pole solution has the highest peak power at the base speed of 280 kilowatt and the highest continuous power at the maximum speed of 110 kilowatt. Its efficiency is in the middle of those of the 4-pole and 8-pole solution with a value of 97.6%. For this reason, the 6-pole solution has been considered as the best candidate for further refinement. In order to guarantee the structural integrity at high speed, the radial ribs have to be introduced. The introduction of radial ribs degrades the performance of machine. Larger are the radial ribs and tangential ribs, and lower is the silencing ratio of the machine, and so higher the degradation of the performance. In order to minimize the mass of the tangential and radial ribs, guaranteeing the structural integrity, a topology optimization is used. The topology optimization is a tool commonly used in mechanical design that is able to minimize the material needed to withstand the mechanical load. The study of the topology optimization has been carried out on the 6-pole design. Therefore, a further magnetostructural optimization has been carried out on the shape obtained by the topology optimization. The results of the process has led to a new rotor layout with asymmetric shape and multiple ribs in different positions with respect to the flux barriers. These multiple ribs connect the segments to each other axially and transversally. It is worth noting that this procedure leads to a quite unusual design compared to those reported in literature. The rotor has also two asymmetry. Two consequent poles are different, and there is another asymmetry in the pole. Respect to the q-axis, the blue line, the pole is not symmetric. These two asymmetry has been introduced in order to minimize the torque ripple of the machine, but this kind of asymmetry produces a different behavior of the torque for the motor operation and brake operation. The figure shows the final design as a cross-section of the stator and the rotor core. The used electrical steel for this application is the M235-35A, with a thickness of 0.35 mm. The stator has 54 slots. The final design is able to satisfy all the requirements. The specific peak power is widely satisfied, and the specific peak torque is satisfied with a value of 8.4. The mass of the active parts and the peak efficiency are also satisfied. The active parts weight is 46 kg, and the peak efficiency is 96.4%. The table shows the performance of the machine and the losses for the peak operation mode and for the continuous operation mode. The power factor of the machine is low, but these are two very critical points. In the peak power, the machine reaches very high level of saturation, and at the maximum speed, the motor works in a deep flux weakening condition. The torque ripple is low, considering the type of machine, 4% in the peak power operation and 10% in the continuous power operation at the maximum speed. The skew angle is set to the angle of the stator slot. The figures show the results in terms of efficiency maps. On the left, there is the torque versus speed, and on the right, the power versus speed. The efficiency map shows a high efficiency for medium torque, medium power values, and medium speed. The maximum efficiency is higher than 96%, and in purple is highlighted the value of the torque and the speed in which the motor works in the WLTP cycle. The figure shows the mechanical analysis of the final solutions in terms of equivalent stress. The distribution of the stress in the ribs is homogeneous, and the tangential ribs are quite unloaded in terms of mechanical stress, but they can be thin. The tangential ribs work in bad direction respect the centrifugal forces, and the topology optimization have moved the radial ribs from the center of the barrier toward the tangential ribs in order to help the mechanical integrity. The ribs maintain enough mechanical integrity in the rotor structure when rotational forces are applied at high speed, 80,000 RPM, satisfying the mechanical limits of the chosen electrical steel. The lower power machine, the 75 kilowatt, has been scaled from the 200 kilowatt design only by changing the stator winding and the stack length, but using the same housing. The 75 kilowatt solution has a lower bus DC voltage and a lower speed. This scaled version will be integrated on the vehicle powertrain for performance testing. The figures show the manufacturing of the electrical steel of the rotor and its assembly. The pictures are a courtesy of LCD. The figures show the realized prototype for the two sides of the motor. On the left, there is the 200 kilowatt motor, and on the right, the 75 kilowatt motor. The motors has the same cross-section with different lengths. On the other end, this figure shows the motor on the left, the housing on the right, and below them there are the DC capacitor, the SiC module, and assembled power electronics. The figure shows the integration of the motor with the power electronics. The motor and the inverter share the same liquid cooling system. In conclusion, the innovative proposed synchronous reluctance motor fully satisfies the requirements and appears to be a good solution for automotive applications. The mechanical finite element analysis has pointed out no critical stress at high speed, with a reasonable deformation with respect to the air gap dimension. The result confirms that the rotor structure is able to withstand the mechanical stress at high speeds. From the 200 kilowatt design, the lower power machine, the 75 kilowatt, has been scaled only by changing the stator winding and the stack length. Since the 75 kilowatt motor has a lower operating speed than the 200 kilowatt motor, its design satisfies the mechanical limits as well. The 75 and the 200 kilowatt synchronous reluctance motors will be tested later this year, COVID permitted. Thank you for your attention.
Great, thank you very much, Andrea, for your interesting presentation. Good, so let's meanwhile launch our next poll. And meanwhile, I will invite Andrea to start sharing your presentation. And meanwhile, you're invited to emit your votes on the following two questions. So what aspects of the pure synchronous reluctance machine are the most attractive to you? Low inertia, mass, simple manufacturing, cheap motor solution, very low losses in the rotor, easily recyclable rotor. And second question, what's the most relevant drawback of the pure SynRel motor? So low flux weakening region, low power factor, low power to weight ratio compared to PM machines, very low losses in the rotor, also at high speeds. Oh, sorry, I think there is a mistake in the last two. questions. So yeah, for the second question, just consider the three first choices. I think the other are a mistake from the previous one, from the previous question. Good. So hereby leaving a few more seconds for your votes, and then we will comment on the results shortly after. So once all the presentations have been made. Okay, good. So let's see the results. We will comment on the results later on. Thank you. So let's now go with Andre. Please, the floor is yours. You can go ahead. Thank you.
Thank you, Fernando. Hello, everyone. My name is Andre Nasr. I'm an electrical machine design engineer at IFPN in France. I will be presenting today the design of a permanent magnet synchronous reluctance motor using ferrite magnets. So my presentation will be divided into two parts. In the first part, I will be comparing neodymium magnets and ferrite magnets. So those are the pros and cons of using ferrite magnets in electric motors. And in the last part, I will be presenting two electric motors that have been designed at IFPN for the ReFreeDrive project. So let's begin by comparing the characteristics of neodymium and ferrite magnets. So we all know that neodymium are the most powerful magnets in the market today, with an average BR of 1.2 Tesla. They also have a high coercitive magnetic field. So I'm talking about the HCJ. On the other hand, ferrites have relatively low magnetic properties. So with an average BR of 0.4 Tesla. So comparing with neodymium magnets, we have 1/3 of the BR. They also have much lower coercitive magnetic field. When I'm talking about the coercive magnetic field, so having a high value, it means that the magnet is more resistant to demagnetization. One advantage for the ferrite magnets is that they don't need any surface protection, unlike neodymium magnets that need such protection in order to prevent oxidation. But maybe the biggest advantage of ferrite is their price. So we all know that ferrites are inexpensive compared to neodymium magnets. They maybe have 10 times less cost. They cost 10 times less than a neodymium magnet. But the high cost is not the only problem for a neodymium magnet. In general, all rare earth materials have an uncertain market and uncertain future, let's say. So this is what makes their cost volatile. So that's why we can find today a lot of work, a lot of research that is being made in order to improve the design of electric motors without using rare earth materials. And at the end, I want to discuss a little bit about the manufacturing of small magnets. So there is no particular problems with manufacturing small neodymium magnet, but it's not the case for ferrite magnets. When you want to manufacture small ferrite magnets, the machining costs are much higher. So as we have seen in the previous slide, a neodymium motor will always have better electromagnetic performances than a ferrite motor. But the question is, how can we reduce this gap in performance? The answer has actually two parts. So the first part, it's about the motor technology. And in the second part, it's about the application itself. So concerning the motor technology, I will give the example of two electric motors. So on the left, we can find a permanent magnet assisted synchronous reluctance motor, and on the right, we have a surface mounted permanent magnet motor, so a SMPM motor. So we all know that a synchronous reluctance motor have reluctance torque, so it is torque without using magnets. In such a machine, we have almost 60% of the total torque, which is reluctance torque, and only 40% is torque which is generated from magnets. On the other hand, if we take the SMPM motor, we have 100% of magnet torque. So if we do a small comparison, if we want to use ferrites in both motors, we can clearly see that in the we will have a higher impact in the SMPPM motor. So yeah, we should choose the right technology. Motor technology is very important when we want to use ferrite magnets. And concerning the other part of my answer, it is the application, and it is more about the motor size. Let's take an example. If we have a reference motor which was designed using neodymium magnet, and we want to design an equivalent motor using ferrites instead. The problem is when the motor is small, the size is small, we need to use small magnets, small ferrite magnets. And as I have already mentioned, when we want to manufacture small components, small ferrite magnets, the machining costs are much higher compared to neodymium magnets. So in this case, we will lose the price advantage of ferrites. So as a conclusion of this couple of slides, so we can't use ferrites anywhere we want. So we should really pick the right motor technology and also the right application. So at the end of this part, I want to present a comparison between a neodymium motor and a ferrite motor. Both these designs have been made for a B segment application. So it's not a secret that using ferrite magnets, we will have lower performances. In this case, we have minus 15% of maximum torque. We have minus 17% for the maximum power, and we will lose even more at maximum speed. But if we take the cost into account, we'll see that we can save up to 25% of cost per Newton meter and per kilowatt, which is a big difference and can make the difference in such application where the costs are very important. So yeah, as I have already said, IFPN have designed two electric motors for the ReFreeDrive project. So we have a 75 and a 200 kilowatt motor. On this slide, you can find the requirements. So we have the specific power, the specific torque, the active parts weight, the maximum speed, which is between 15 and 18,000 RPM, and the efficiency, which should be higher than 96%. So let's start by presenting the design of the 200 kilowatt motor. So for this design, we have used a Macaron rotor design. The number of pole pairs is equal to 5. We have a SPP equal to 2, so the number of slots per pole and per phase. We have used 7 ferrite magnets in each pole, and we have an inner gap of 0.6 millimeter. So on this slide, we have some of the performances of this motor. So with 800 volt and for 416 ampere RMS, we were able to achieve 405 Newton meter for the maximum torque. We have reached a maximum power of 226 kilowatt and a maximum efficiency of 96%. All of that with a weight of 46.1 kilogram. You have also on the slides the specific torque and the specific power. So now let's talk a little bit about the design of the smaller motor, the 675 kilowatt motor. What is special with this design is that we have used scalability. So we have the same housing between the 200 kilowatt and the 75 kilowatt motors. We have also the same rotor and the stator. We have, of course, the same magnets, which is a big advantage. And also we have the same mechanical parts. What has changed between both designs are the voltage, of course. We have also reduced the active lengths, and we have increased the number of turns by 1. Once again, I present here the performances of this motor. So we have a maximum torque of 148 Newton meter, 88 kilowatt for the maximum power, and a maximum efficiency of 95%. You will also find on the slide, we have the weight, the specific torque, and the specific power. So at the end of this presentation, just a word about the prototypes. So all the prototypes have been manufactured by Mavel, and the testing has already begun at IFPN facilities in France. Thank you all for your attention.